Assalamu alaikum. Dear students, in this video related to my lectures on probability theory, I'll be talking about the term moments. We'll try to understand these mathematical objects, and then in lectures to follow, we will try to understand the advantages and the interpretations of these mathematical objects. So what is moment? So we will go to its mathematical definition, and then we will try to identify the similarities of these moments with the existing concepts. So the moments, so for example, the rth moment about region of a random variable x, and we denote it by mu r dash, is the expected value. Please remember that we have already in my previous lecture we spoke about the expectation and related concept. So we are when we talk about these moments, these are basically the expectations, and the rth moment about region denoted by mu r dash is nothing but this is expectation of the random variable x to the power r. So this is expectation of this random variable with its rth power, and this obviously will be defined by this is summation x to the power r f of x, and obviously this summation suggests that the random variable chosen is discrete, and this r can take different values, and with these different values of r will give us different objects which we may already know or which will be used for in the lectures to come. And then if x is a continuous random variable, then this mu r dash will be this integral from minus infinity to plus infinity x to the power r f of x dx. So now we know this mathematical object's moment about region, we will denote it by mu r dash. And why we put this dash? This is to differentiate it from the moment about mean. We'll be also talking about the moment about mean. So we'll be talking about two kind of moments, one about the origin and one about the mean. So the rth moment and the rth moment about the mean of a random variable x denoted by mu r. Now we have eliminated the dash, is the expected value of what? Now we have a new random variable, this x minus the mean to the power r. So when we define it, this is something very similar to my to the previous definition, but now the difference is that we have defined the subtraction. So x minus mu to the power r and the expectation of this object. So expectation of x minus mu to the power r, and then this becomes this summation x minus mu to the power r f of x, and obviously r can assume all values from 0, 1, 2, and this summation suggests that the variable I am taking is discrete, and when this will be continuous, this will be defined as always, but now we will be using integrals. I'll go back and I'll be talking about my moments about region, and to begin with, if I talk about this mu naught is what I am taking this expectation for to the power 0. Now when I take to the power 0, so this becomes 0, so this whole term will vanish, and when this whole term will vanish, I will have nothing. I will have this summation, nothing but this summation with respect to x, and this is sum of probabilities, and then the sum of probabilities will be 1. So over there you can see that this mu naught dash is 1. And what will happen when r is 1? When r is 1, we put r1 over here, and we will be having this summation about x, and this x f of x, and this is the routine expectation. And then this routine expectation we start calling it mu. So this is this summation x f of x, and this is mean of the random variable x, and we will denote it by mu. And over here we are using the same mu, the same average. Now over here, if I consider r equals to 1, if I consider r equals to 1, I take this power, and this power eats it up, so this term will become 1, and then this will have, this summation will be only x f of x, and this summation will be about this f of x only, and this again is sum of probabilities. So again, like the previous case, mu 1 dash, mu naught dash, and mu naught, they are both 1. This is actually the sum of probabilities. And over there we had mu 1, that was mu, and now if we consider mu 1, that means we are considering to the power r. So this is x minus mu f of x, and if I operate it, so this f of x, and with this whole summation, this is a familiar object, this is mu, and then this mu will go out, this is a constant by using the expectation property. So and this summation will come inside, and this is x f of x, and this whole thing will become 1. So I'll be having mu minus mu, and this whole thing becomes 0. So that means this mu1 will be 0. And what will happen with mu2? This is the famous object. This is a term which will be used a lot. This is variance, and this is my second moment about the mean, and we will denote it by mu2, and this is variance, and we'll be writing it variance of x, and if I take its square root, this will become the standard deviation. And this is another term, variance and standard deviation. We will be using these terms in this course of probability very frequently. And what is this variance now? What is this variance? Denoted by this sigma square. This is mu2 dash. This is the second moment about the origin minus mu squared. And how we obtain this? The proof is rather simple. This is expectation of x minus mu whole squared. I simply open up this square, and this becomes x square minus 2 mu x plus mu square, and then by using the properties of expectation discussed in our previous lecture, this becomes expectation of x square minus 2 mu, these are constant, and then this is expectation of x, and then expectation of constant is constant itself. So expectation of this mu square is mu square itself. So this is mu square. And now this is expectation of x square minus 2 mu square. Why this is 2 mu square? Because this is also mu. This is mu times this mu, this becomes mu square. Plus mu square, so this becomes expectation of x square minus mu square. And this expectation of x square is nothing but the second moment about the origin. So this is mu2 dash minus this mu square. And what is this variance? This actually tells us about the spread of that. This tells us about the spread of the distribution of the random variable, that how our data will be distributed. So if this variance is higher, so that means that there is the greater probability of getting a value not close to the mean. So that means we will be moving away from the mean. So higher variance will mean that our data will be spread, and the data will be spread. And the smaller value of this variance will suggest that data will be the spread of data will not be that big, and it will be closer to the mean. And this mu3, another term which we may use in our course, that indicates the lack of symmetry. This mu3, this is lack of symmetry, and we also call it skewness. What we'll do is we will continuously try to develop the mathematical objects. We'll try to define these various notions, and once we develop these mathematical objects, these mathematical notions, then we will take real life examples. We will try to model those problems. Then we have this existing literature. We'll try to identify the similarities and differences. So if someone in a lab has all the data, and he wants to get that data analyzed, so we'll be computing all these values, and on one hand we have the standards, on one hand we have the real data. So in order to interpret that real data, we will be talking about this real data in terms of the hypothetical setting we make. So this all is the mathematical setting which may be useful for our description of several problems related to applications from different fields of science. And so we'll continue to have the debate over all those topics. So about the moments, we will have one more lecture, and then we will be using all this in our lectures to follow. Thank you.